Having completed the section on air masses, let's now focus on fronts. Fronts are transition zones between air masses of different temperature, namely polar and tropical. You may recall from the pressure systems lesson that a frontal boundary exists between polar maritime air and tropical maritime air, as you can see here. This is called the polar front. We will concentrate on the polar front for the remainder of this lesson. This frontal boundary is very fluid, and when warm air moves northwards to replace heavy cold air, pressure is reduced. As air along the surface moves towards the low pressure, it is deflected to the right by Coriolis force. This flow of air creates two unique frontal features, a cold and warm front. Along this part of the polar front, cold air is being forced against warm air and undercutting it. This is called a cold front. It is shown here in cross-section. Along this part of the polar front, warm air is being forced up and over the colder air the other side of the front. This is called a warm front and is shown here in cross-section. To get a better perspective of what the whole system looks like in cross-section, for example the warm and cold front, let's briefly return to the polar front depression again, looking at the plan view. These systems are found between 35 degrees north and 65 degrees north and move from west to east across the Atlantic and Pacific. What we need to understand in more detail is what weather conditions we might expect if such a system were approaching the British Isles. The fronts will normally arrive in sequence. The warm front first, followed by the cold front. On the plan view, we can draw a line which cuts through both cold and warm fronts, and we can then look at the cross-section as shown here. The warm front will be the first of the fronts to influence the weather as the system moves from left to right. The slope of a typical warm front is 1 in 150. It is very shallow, and the cloud that develops is mainly stratiform type. However, the first clouds noticed by an observer on the ground will be very high altitude cirrus, then cirrostratus. Eventually, as the front gets closer, thicker altostratus will be observed, and eventually, where the front meets the ground, the nimbostratus will prevail. The whole sequence may take up to 12 hours to pass over a location. The cloud ahead of the warm front can extend for about 600 nautical miles ahead of the surface position of the front. Notice how the main area of precipitation starts some 200 to 300 nautical miles ahead of the surface front as the base of the cloud gradually lowers. This can persist for many hours as the front gets closer. As the precipitation increases closer to the ground position of the front, visibility will reduce, and eventually frontal fog may be observed. We've considered the cloud ahead of a warm front, but what happens to the other elements of the weather? First, let's look at the wind. To see this, let's return to the plan view. Ahead of the warm front, notice that the wind is fairly light, coming from about 250 degrees. But, as the front approaches, it does change. It slowly increases in speed and blows from about 200 degrees. So with the approach of the warm front, the wind backs slightly and strengthens. To summarize, these are the conditions that you would expect to observe at the surface with an approaching warm front. The cloud will increase and the base will lower. Precipitation will set in, becoming persistent and moderate in intensity. The wind will back and increase in strength. The visibility will deteriorate. The pressure will fall steadily. The temperature will remain at a fairly steady low value. The dew point will usually be steady and fairly low. Next, we shall consider the weather expected when the surface warm front arrives. as shown here on the plan view and here on the cross-section view. The cloud will be low and remain fairly constant. Precipitation will be continuous and moderate, perhaps heavy. Looking at the plan view, you will notice the wind changes direction quite markedly from here, just before the front, to here, just after the front. We see here a sharp veer in the wind. Any sudden change in wind direction near the surface needs to be planned for when you are flying because of the changes in heading that this will necessitate to maintain a fixed track. Visibility will be poor with widespread hill fog developing. The pressure will continue to decrease slightly. The temperature and dew point will suddenly rise as we enter the warm tropical air. This warm air between the cold and warm fronts is called the warm sector. As we have just learned, the warm sector lies between the fronts. This is a stable air mass, and the weather is usually fairly consistent throughout this section. It is characterized by a fairly uniform base of extensive stratus or stratocumulus cloud, with the possibility of light drizzle. The wind will be steady and often strong. The visibility can be poor, with extensive fog over high ground. Looking at just the plan view, you will notice that in the warm sector, as we approach the cold front, the pressure continues to fall slowly. Lastly, the temperature and dew point will remain fairly high and steady throughout this warm, moist air mass. Now let's look at the cold front, which will follow behind the warm sector as the system moves from left to right. A cold front is almost a warm front in reverse, but note that the average slope is a little steeper, usually 1 in 50. The cold air advances and undercuts the warm air, forcing it aloft, causing the air to cool adiabatically and condense. The main cloud is still stratiform since the slope is still very shallow. However, as you may recall from the pressure systems lesson, the nose of cold air here creates very unstable conditions, and air rises very rapidly, creating large cumuliform clouds ahead of the surface position of the front. This makes the passage of the cold front quite sudden with little warning that it is approaching. These cumuliform clouds can create dangerous squall-line thunderstorms. It is highly recommended that you never fly through a cold front at low level, no matter what your experience or capability. Watch the weather immediately ahead of the cold front very carefully too. To summarise then, these are the conditions that you would expect to notice at the surface with an approaching cold front. Expect embedded cumuliform cloud within the stratiform cloud, giving steady and showery precipitation. The wind will veer sharply with gusts, and squalls are also a possibility. Before the front arrived, the surface pressure will fall, but will rise once the front has passed. In the precipitation, the visibility will be poor, but will quickly show signs of improving. Lastly, the temperature and dew point will usually fall sharply as we cross into the cold air behind the front. Once the cold front has passed, the weather will be dominated by the conditions behind the cold front, as shown here. In this area, notice that cold polar maritime air is moving towards the equator and is therefore travelling over warmer surfaces. You may recall that this creates instability and therefore isolated cumuliform clouds will develop behind the cold front. The pressure will continue rising with the visibility good, though it will deteriorate temporarily in the showers. Remember, even though the dangerous conditions of the cold front have passed, do not presume that the conditions will improve significantly. You may still find significant weather after the cold front, as we have shown. Having seen the weather expected with the passage of the polar front depression, we will now examine how it is possible to calculate the movement of the fronts themselves. The speed of movement of a warm front can be estimated using a simple technique. All you need is a weather chart with a geostrophic scale on it. Measure the isobaric spacing on the front like this. Use that measurement on the geostrophic wind scale and then multiply the answer by 2/3. This gives the approximate speed of the front. Having seen how to calculate the speed, let us look at the direction. The front will move in the direction of the symbols, but more accurately, it will move parallel to the isobars behind the front. The speed of movement of a cold front can be estimated in a similar manner to the warm front technique. Again, measure the isobaric spacing on the front like this, and use the geostrophic wind scale. This gives an approximate answer for the speed of the front. The direction of the cold front will be parallel to the isobars behind the front. Of the two types of fronts we have seen, the cold front is the faster moving, and it will eventually catch up with the warm front, as we see here in plan and profile views. When the two fronts meet, they merge and create what is known as an occluded front. Notice that to identify this new front, both the warm and cold front symbols appear together on the frontal line. However, as you will now see in the cross-section, they can merge in two ways. If the cold front goes up and over the warm front like this, it is called a warm occlusion. However, if the cold front goes underneath the warm front like this, then it is called a cold occlusion. The weather of the occlusion is a combination of the warm and cold front weather. This is typically long periods of continuous rain interspersed with heavy showers. Occlusions in the United Kingdom are responsible for most of the major flooding events over recent years. There is one last front to examine before we complete this lesson. Let us return to the polar front boundary we observed at the beginning of the lesson. There is little interaction between the warm tropical maritime and polar maritime air, then no kinks or disturbances will be observed. This is described as a stationary front, and the cold and warm front symbols will be shown like this to signify the static boundary. Note though that the winds will blow parallel to the frontal position as shown. That completes the lesson on air masses and fronts. It is a very important part of aviation meteorology, and it is vital to understand the various points that have been brought out through this lesson. The passage of fronts has significant implications for private pilots. Pressure and temperature changes can cause altimeter altitude errors of up to 1,000 feet or more. Crossing any front will inevitably lead to flying on instruments, and combined with wind changes, this could be dangerous for an inexperienced pilot, even one with an instrument rating. When fronts are present, pre-flight planning needs to be especially thorough and detailed if the fronts are to be avoided or negotiated.